Shortly about me, I spent more than 18 years working with Oracle, and we had to squeeze out every bit of performance and had to come up with creative solutions for the real-time payment card processing. So we worked with all kinds of technologies, like old spinning disks with like consumer-grade IDEs, and then the commercial kind of enterprise-level SCSI setups, different RAID configurations, network-attached storage, and then finally SSDs came out, and then it was like, oh, well, our job is done, so it runs pretty fast. It should be good. So now I work for a different company, and we use RDS in AWS, and guess what? We still struggle with query performance, and I guess most of people do as well. Before I go forward, I hope you can read, the letters are quite small, but I mean, the correct answer to the question, how do you improve database performance, is always, it depends. So I'm showing you this because I will try to give you more specific suggestions that might work in 95% of cases, and if you find some of those 5% cases, then don't blame me. I warned you. So let's go into the topics. And all this came out of trying to optimize some queries, and I discovered some new things about Postgres for myself. So, but first, let's go into theory a bit to understand how the database thinks. So all data inside the database is stored on the disk. It's called a heap. It's organized in blocks. So blocks in Postgres typically are 8 kilobytes. And this block contains rows. Sometimes rows might span multiple blocks. But the idea is that these are blocks, and they are on the disk kind of sequentially. So if you know something about the hardware, then reading something sequential from the disk, from the memory, is always faster than just jumping around. It was true for the spinning disks, and it's, to the lesser extent, it's still true even for SSDs. So whenever a database has to find something, it has to scan through the whole data inside the table. So it's not fast. So what's the solution? The solutions are indexes. So these are not binary indexes. These are balanced trees. And this is like a quick lookup structure. So it works for, just to be clear, it works for equality and greater than, less than comparisons. And how it works, so there's a tree. So if I want to look up key, let's say 18, then I start at the root node. I have to find an entry at the root node that is the largest value that is still less or equal to the one that I'm looking for. In this case, it's 15. It says me that I have to jump to the right node. I go to the next level, and there the value that is less than or equal to what I want to find is 17. So, and then this middle pointer points me to the block, and inside the block, the database goes through all rows until it finds the one we are looking for. Yeah, so just a quick note about what is stored inside the data. For a lot of databases like Oracle and Postgres, it stores some kind of identifier of the physical block where to find the row. There are databases like MySQL where all data, so they do not have the table as a heap. Their data is organized in the index structure based on the primary key, and then these data parts contain the whole row of the data, and secondary indexes in that case just contain the value of the primary key. So secondary indexes in MySQL do like 2 index lookups. And yeah, so here it points to some data block, and inside data block you can find the value 18. So this is how it looks in for a single row. In practice, if you look down at it, and especially it's for the Postgres, because Postgres doesn't update any row in place, it always appends new versions of the row, and then it does this vacuuming, which moves data around. So typically you end like with a complete random. So there's no, it doesn't preserve the insert order or anything like that. So this brings us to how the database chooses between going through the table or using the index. There are two main parameters. So one is the sequential page access cost. So how much does it cost to read a single block in a series of multiple blocks? So it's typically 1. So it's kind of the base value. And then there's the second one, which says how much does it cost to access a random page. If you think back to the spinning disks, you had to spin up the disk and then move the head to the specific location. So definitely it's much slower than just reading the next block that follows. So the cost there is 4 by default. And in documentation, it says that the actual cost is closer to 40. But the Postgres assumes that 90% of the random reads will go through the cache. So therefore, it's 4. And in the same documentation, they suggest to have 1.1 for SSDs. So that's the documentation. Now we have Postgres in AWS. Can you guess what is the cost of random page access? No, it's 4. It's the same default. So inside AWS, and I mean most Postgres instances work as if they would be running on a slow spinning disks. And then there are some other costs which Postgres uses, but those are, compared to these page access costs, those are like minimal, so we can ignore them. And the choice between the index and table scan is mostly based on those page costs. So whenever I ask, for example, in this my demo case, I ask for all values between 17 and 21. And then the database thinks, so the database estimates, tries to choose which access plan would be faster. So if it thinks about scanning the whole table, it knows the number of blocks it would have to read, and it quickly calculates that it would cost it 8 parrots, or whatever the unit is. In similar way, just for a reminder, this is how my example setup looks like. If I want to read the same from the index, so the quick estimation, so I'm leaving out the costs for accessing the index itself, so that's a separate topic and that's complicated calculations, but it doesn't affect the main idea. So if the database thinks that it will have to access 4 rows through the index, so it will have to read 4 blocks, so it calculates costs by random access, and quickly already on the 3rd row, it thinks that, oh, it will be much more expensive. So of course, this is a small setup example, but just to give you a quick idea how database thinks internally. So from these costs, then, I mean, it should be obvious that accessing a single record should be faster through index, because and although it pays these random costs, it's single index, so it should be faster. Accessing the whole table should be faster through scanning the whole table, because it's sequential costs. And then there's something in the middle. So most materials say that it's a single-digit percentage. So if you are accessing, let's say, up to 2-3% of the whole table, then it will be faster through the index, and for the rest, it's faster just to scan the whole table. And this boils down to this sequential versus random access, which is 1 to 4. And then there add to that access and reading the index itself. So that's the reason why database often chooses to skip your indexes, even if you have them. And then the other observation is that database is often bad at estimating those numbers. And sometimes it's that the developers know better. Quickly, so also for creating indexes, so just because each index has its own kind of, each index has like initial cost to use it for the database, then of course, database would prefer single multi-column index instead of multiple indexes. So it's hard to force database to use multiple indexes on the same table. And the typical advice is to index high cardinality columns and not to put indexes on low cardinality columns. So high cardinality might be your phone number, email, if it's like a user table. For low cardinality from financial institutions, so might be like true, false, or even the currency code, because those currencies are very skewed. So typically USDs and euros are the majority of transactions. So if you have low cardinality, in case of Postgres, then probably partial index might be a better fit, just to kind of, if I look at the database and I see that there's an index on the low cardinality column, but it's a partial index, then I kind of assume that developer knew what he was doing, he or she. So that's kind of theory, but let's practice. So I use Django here, but I mean, it applies to all programming languages. It's just a bit different syntax. You can do the same from SQL prompt. So what I have here are two tables. So one is the member table. So most importantly, there's the name with index on it. And then there is document in one of three states. So it also has an index. So it should be probably like a partial index, but I will show how I need it like this. And then I have a JSON field because I want to show you how to create indexes in JSON as well. So now I generated some data. So I think I started with 10 rows. It didn't work as I wanted it to work. Then I generated like 3 more thousand and probably some more thousands. And the main key takeaway here is that in a perfect world, you would try to optimize queries on a clone of your production database because it has the right amount of data and it has the right distribution of data. And as close as you get to it, the better. If you need to have like some private information removed, fine. If you can like get it as close as possible, that's also good. So we have some data. Let's do some queries. But first, like how to understand how database is thinking how it will execute the queries, because the queries are written in like declarative language, and it's up to the database to interpret it. In Django, there's this QuerySet.explain. From the SQL prompt, you just can simply write explain and then the SQL query. So the most simple example is like this. So you have some, so this is Django ORM query. You put explain there and you print the result. So it says that it will use index scan on this, using this specific index on that table, and that's the index condition, which basically describes kind of what the index contains. So what's most important is that it also writes, kind of prints out the costs that the database estimated, how much it would cost. But remember, those are just estimates. So much better way is to add this analyze equals true, which will cause the query also to be executed. And then once it's executed, you also get the actual time back, the actual number of rows, and what's more important, you get the execution time. So there are a lot of cases where database thinks that the cost actually will be much, much higher than it is. So if you do some tuning, you should be looking at this execution time instead. Now, just another example. So I'm doing like case-insensitive search here, and it says that it will do a sequential scan on the table, and the filter condition is this upper name, so on. And in a nutshell, so if it says sequential scan, so it means it's going through the whole table, and what it writes on the filter, it means that the database failed to find index for this index scan, then it's good most of the time. There is, for me as an Oracle guy, it's really strange that Postgres actually stores index null inside indexes, so that was a big discovery for me, but it does. However, although we have index on this column and we have condition on this column, so database doesn't use index here, you could probably see it also from the costs because it estimates that it will return quite a lot of rows. But I mean, the external ID is kind of, it has high cardinality, but the problem is that although the field itself has high cardinality, the expression itself is low cardinality. So what are the outcomes? True and false. So it's Boolean 50-50 on average. And there's this interesting talk I saw at the Django Con. There are some implications of Postgres storing null values inside the index, so it makes indexes unnecessarily large. So if you have time, look at it. So better handling of null indexes, I like to use conditional indexes, but I create indexes on some other field and then add this is null as an additional condition. I like to do conditions on soft delete so that the index contains only the rows that are not soft deleted. And the favorite one is that on some date, let's say I have a page where I have to display the events for the last week or last 2 weeks, then I create index that includes only the last month, and then I recreate the index once in a while, and so it gives me quick access to the last week's data, although the table might contain, I don't know, even years of data. And yeah, so I created this index, and yeah, so it's now, although we have conditioned on the name and external ID, the index itself, the index condition is only on the name, and then Postgres knows implicitly that this index will contain only the rows that with external ID equals null. Then another thing I want to show is about, so we had 3 document statuses, unknown, valid, and invalid. So I have worked with distribution of data, so the database estimates it will get only around 93 rows with status unknown. So if I do this, it says that, okay, it will use index, all fine. However, a lot of times I see in the code things like that, so exclude. So the thing is, indexes do not work for negative expressions. It works for equality, greater than, less than. It doesn't work not equal. So if I see a query that is doing just the exclude and not a filter, it's a red flag, because database doesn't know that, so it can't use the index. It will go through the full table scan, although it will return exactly the same row set. So a quick fix for that is to calculate the kind of positive query inside the code. So I calculate for statuses which the query applies. So I get all possible values, I subtract the values I do not want to see, and then I filter kind of on a positive condition, and then it can use the index. So now let's create some indexes. So first, I had this case-insensitive query. So typically what people say, oh, well, I have an index on this name field, why database isn't using it? Well, because database is looking for upper on the name, so it's not the same. So for us, it might be, oh, it's approximately the same, but it's not for the database. It wants to see exactly the same condition. So how to do that? So we saw that database is looking for upper on the name, so I have to create index which says upper on the name. Once I do this, database can use the index, and it's all fine. So now the query uses indexes. Now, closer to the problem we had, so what we were doing, we were doing like live search queries. So as soon as you type like 3 characters, it starts to return results from the server. And how you do that in Django is you use this iContains. So it goes back inside the database, it executes as, so it looks for upper on the name and these two symbols, which in other databases they stand for like operators. So we have index on the name, we have index on the upper of the name, and it's still not using index. So what's the problem? The problem is that for this kind of like expression, database Postgres can't use this B-tree index, so you have to create a different kind of index. So it's gin index. So way you do it in the Django, so there's a lot of boilerplate. You have to include this package inside your applications. Then you can create a gin index with operator class on the upper of the name, and then some other boilerplate. So trust me, it's much easier to do that in SQL, but you have to, since you work with Django, then you have to follow this stuff. And then one more thing to make it work, you have to install this trigram extension, so you can do it once in your whatever migration file, and then it will work. So you can create the index. So I have created the index. I run the same query, but it doesn't work. Any ideas why? Well, the fix for this is to analyze the table, because database doesn't have statistics and it doesn't know yet about that index. So this is typical failure when you try to optimize create new indexes and the queries are not working faster. So it's often you have to analyze table after each creation of the index. And once I did this, so now it's great. So it uses our newly created index. Yeah, and it uses that for case-insensitive queries. Now, what if I want to do like case-sensitive queries? It can't use it. So the main point here is that it's looking for the exact type of index and for the exact condition that is there. So we do not have gin index on the name itself. We have gin index on the upper of the name. So now let's do JSON. So in Django, it's quite easy to work with JSON. So you just do 2 underscores and you can address the fields inside the JSON. So something like this, and I try to do the same case-insensitive search inside the JSON field. This is the query. So from all the previous examples, I know that I have to create gin index on upper and whatever this JSON field is. So this is how you create it. So this is by trial and error inside Django. So I had to add cast because otherwise it would fail at the SQL execution stage. So Django itself didn't complain, but it complained later at the database. So this is how you create index on the JSON field. Now, the index is created, but still no improvements. Any ideas why? I did analyze the table. So this was a bit like brain teaser. So if you look at the index and at the condition that database is trying to execute, and you should pay attention to those 2 parts. So on the upper one, it says retrieve whatever JSON object is with this key. But when executing the database query, it's looking for specifically string type. So it returns only the string elements, named document type, not whatever integers named document type or JSON objects named document, no. So how to fix this? So I gave up on Django. So this is how you do it in SQL. So for me, it's much, much easier and much more understandable. So I created the index. And we will go with, I know we are out of time, but we will go for 5 more minutes quickly. So we fixed the query. So now it's using the index. And now the exercise of putting it all together. So we are doing live search on something like 10 different fields on 4 tables. I managed to reproduce it on a 2 table and 2 field example. So we are filtering on the name and filtering on document number. So we just created the indexes for these specific kind of operations. And what we are doing, we are looking for members that match either the name or the member has a document with this specific string. So let's see how database will execute it. And so although we have indexes, it's not using indexes neither on the member, neither on the document table. So what's happening? Well, Postgres is being a bit stupid. at this point, so I think the version 18 promised that there are some improvements for the scan4 queries, so I haven't tried it out yet, but hopefully it does. So I know that in Oracle, these kind of queries work like charms, so Postgres got me surprised here. So what you have to do for Postgres is to do actually more work. So you execute name filter separately, you execute document filter separately, and then gather the member IDs from both of these queries, and then run the query on those IDs. So this looks like really, really scary. But however, if you look at it, so it's executing much, much faster. So like 5 times faster. It's using index on the document number. It's using the index on the name. And yeah, there's possibilities for optimization, so you do not have to do joins. So we actually ended up doing something like this. And that's it. So one reason I wanted to give this talk is there's this research paper, so it focuses on not on Django, but on Ruby on Rails. And it looked what are the typical performance issues, and missing database indexes was the top issue of all web applications using database. To be fair, close second was the N+1 queries, but yeah, still missing database indexes win. And here's a cheat sheet for each specific kind of filter you write in Django. There's a specific index type. So sometimes people create a GenOp class on simple field and then try to use iContains and wonder why the index is not used. So it has to be matched exactly like this. And that's it. Thank you.
Thank you, Aivars, for this masterclass on database internals and indexes. So I recall that you can ask ask questions on pycon.it/slido. We have one question, and we have time for maybe one more. Can or should you run analyze table in a Django migration? And do you also manage your custom raw SQL indexes in Django migrations?
Yeah, so so another reason to do, like, first, I do create indexes, a lot of indexes in with raw SQL. So the reason for that is because I want to use this concurrently feature so that it runs faster and it doesn't block the table. So therefore, there's the feature in Django where you can kind of write your own migrations, replacing the standard SQL. And then, yeah, regarding analyze, so no, I do not run it after each migration, but I know a lot of companies have the night jobs that just run it like during the night. So that's it.
Okay. Oh, we have 2 more questions. Let's see if we manage to do them quickly. What about index on date time columns?
Yeah, so, well, B3 is fine. So because typically you look for the exact or the range. So that the one problem is if you are doing like query so Django allows you to cut, let's say, date and leave out the time part. So that will have problems. So it's better to do like full date time range, like convert your, let's say, year queries into like year, month, day, and some 00 as a time.
Okay, thank you. There's another one. Did you try to analyze queries in other databases like MySQL?
Sorry?
Did you try to analyze queries in other databases like MySQL?
Analyze, yes. Yeah.
Okay.
Yeah. So they have different names for same things, but the basic ideas are the same. So it's either the index or it's database. There are, so like, I don't know, index bitmap scans and index scans. So those are like different names for basically this. So if you do not want to go into like low-level details, it's basically the same. So.
Okay. Thank you, Aivars, again.